হ্যালো হ্যালো, তোমরা আমার কথা শুনতেছো?
জি স্যার, আসসালামু আলাইকুম। শোনা
ওয়ালাইকুম
যাচ্ছে স্যার?
আসসালাম। আচ্ছা, তোমাদের আমি আরেক একটা ইনফরমেশন দিয়ে রাখি, সেটা হচ্ছে তোমাদের নেক্সট ওয়েডনেসডে, দ্যাট মিনস 30 ডিসেম্বর আরেকটা ক্লাস টেস্ট। এটা হচ্ছে আজকের যে টপিকসটা পড়াবো শুধু সেটার উপরে। ঠিক আছে, নেক্সট ওয়েডনেসডে 30 তারিখ, 30 ডিসেম্বর এটা তোমাদের আরেকটা ক্লাস টেস্ট হবে আজকের যে টপিকসটা পড়াবো সেটার উপরে। এবং আজকের টপিকসটা হচ্ছে লাস্ট টপিকস। এরপরে আমি যদি না বলি তাহলে আর ইয়া হবে না, তাহলে আর ক্লাস হবে না। আজকেরটাই হচ্ছে লাস্ট ক্লাস, মোস্ট প্রবাবলি। মোস্ট প্রবাবলি নেই আজকেরটাই। আর আমি যদি বলি যে আমার এই এত তারিখে ক্লাস লাগবে, তাহলে তো আমি তোমাদেরকে সবাইকে জানিয়ে দেবো। ঠিক আছে। আর আরেকটা ইনস্ট্রাকশন যেটা হচ্ছে নেক্সট এসে ক্লাস টেস্টে আমি গুগল ইসে তোমার জুমের একটা লিংক করে পাঠিয়ে দেবো। সেই জুমে তোমরা সবাই লগ ইন করে কিন্তু ভিডিও অন রাখতে হবে। ঠিক আছে, সবারই ভিডিও অন অন রাখতে হবে। সরি, ভিডিও এবং অডিও, ভিডিও অডিও তোমাদের সবারই জুমে অন রাখতে হবে। কিন্তু পরীক্ষা দেবা তোমরা ইসে গুগল ক্লাসরুমে। বুঝতে পারছো? সবাই কি ক্লিয়ার কিনা? হ্যালো,
স্যার বুঝতে পারিনি কি বললেন, পরে আসছি তো।
আমি বলছি যে নেক্সট ক্লাসে, নেক্সট ইসে যে তোমাদেরকে ক্লাস টেস্টটা নিব ওয়েনডেতে, 30 তারিখে যে ক্লাস টেস্টটা নেব, সেই ক্লাস টেস্টটা দেওয়ার সময় তোমরা ইসে জুমে লগ ইন করবা। জুমের আমি একটা লিঙ্ক করে দেবো, সেই জুমের লিঙ্কে সবাই লগ ইন করে সবারই ভিডিও এবং অডিও অন অন রাখবা। কিন্তু পরীক্ষাটা দেবা কিন্তু তোমরা গুগল ক্লাসরুমে। পরীক্ষাটা দেবা গুগল ক্লাসরুমে, কিন্তু তোমাদের জুমে তোমাদের ভিডিও এবং অডিও অ্যাক্টিভ রাখতে হবে। ঠিক আছে, তোমরা সবাই অনেস্ট, আমি বিশ্বাস করি তোমরা সবাই অনেস্ট। তারপরেও একটা রেসপন্সিবিলিটি তো থেকে যায়, তাই না?
স্যার
তো
অডিও অন
সেজন্য আমি
রাখলে
মাঝে মাঝে একটু
অনেক নয়েজ হয়ে যাবে স্যার।
নয়েজ হবে কেন? তুমি যখন ক্লাসে ক্লাস টেস্ট দিতে তখন কি নয়েজ হতো? হ্যালো সালেক, নূর সালেক, হ্যালো।
জি স্যার, মানে বাসায় তো থাকি স্যার, আমরা নয়েজ না করলে স্যার আশেপাশে যে লোকজন আছে স্যার, তারা তো সেটা
তুমি
নয়েজ
একটু,
করে হঠাৎ
এটা তো
হঠাৎ।
আধা ঘন্টার ব্যাপার। তুমি একটু তো বাসায় যারা থাকে তাদেরকে একটু বলে রাখবা, অথবা তুমি একটু একটু ইসে যাবা, যেখানে থাকবো সেখানে বলবা যে আধা ঘন্টা তোমরা কেউ আসবে না। এটা কেউ আসবে না। তোমাদের বাসায় যদি বলো আমার এটা কোনো একটা ক্লাস আছে, কেউ আসবে না, এটা আমি বিশ্বাস করি। সুতরাং সমস্যা হবে না।
আচ্ছা ঠিক আছে স্যার।
ঠিক আছে, কারণ এটা আসলে একটু ক্লাস টেস্ট নিচ্ছি তো, একটু মানে তোমরা একটু মেক শিওর করতে চাচ্ছি যে না আসলে তোমরা সবাই ভালো আছো। আর তোমাদেরকে আমরাও তো দেখি না অনেকদিন, একটু দেখলাম ভিডিওতে সবাই কেমন আছো। আচ্ছা ঠিক আছে, তাহলে আমি আজকে ক্লাসটা শুরু করি। আজকের টাইম হচ্ছে লাস্ট টপিকস। আর নেক্সট ইয়ারটা হবে না, ক্লাস আর হবে না আমি যদি না বলি। আমার একটা কল আছে জরুরি কল, পরে কথা বলবো। একটু আমি রেকর্ডিংটা স্টার্ট করতে যাচ্ছি, তারপরে শুরু করি। Okay. So recording is started. So I can start the class. So today I will discuss another new topics. That is strain energy. Energy. So all of you know what is energy. And energy is nothing but a word. Okay. Energy is nothing but a word. And sometimes work is known as energy. So what is work? Work is force time displacement. Okay, force time displacement. That means if a force is displaced from one place to another, if a force is displaced from one place to another, then work will be done. Work will be done, and the amount of force work will be force time displacement. Amount of work will be force time displacement. Okay, so if any body is subjected to any kind of force, if any structure or if any body is subjected to any kind of force, then there must be deformation in the body. There must be deformation in the body, and as the body deforms, therefore the applied force must be displaced. Okay, that means a body is subjected to applied force, and due to the applied force, the body must be deformed, and as the body deforms, so the applied force must be displaced. Okay, the displacement may be considerable or may be very small. Okay, it depends on the applied force, but there must be displacement of the applied force. Okay, so as there must be displacement, so there must be work. There must be work, and that will be force time displacement. Or in this case, displacement is nothing but the deformation. Okay, displacement depends on the deformation of the body. So the displacement is represented by the deformation of the body. So the work will be force time deformation, applied force time deformation. Okay, that is the work. That is the work, force time deformation. That is the external work. And that is known as external work. Why it is external? Because it is done externally due to the externally applied force. That is external work. Okay, and according to the conservation of energy, total energy is constant. Total energy is constant. No energy is what is lost. Okay, so according to the conservation of energy, that amount of external energy or external work will be stored in the body. Okay, that amount of external work will be stored in the body, and that energy is known as strain energy. Okay, so simply, what will be the strain energy? Strain energy is nothing but the energy or work stored in the body due to the applied force. That is strain energy. Okay, so if we look at this figure, it is an element. The left side figure is an element, and this element is subjected to axial stress sigma. Stress sigma, and the dimensions of the elements are delta x, delta y, delta z. It is a very small element, and dimensions are very small, delta x, delta y, delta z. And this phase is subjected to axial stress. So what will be the energy? What will be the energy stored in this element? What will be the energy stored in this element? So energy is nothing but the external work. So we have to calculate the what is the external work, and to calculate the work, we have to know the force and we have to know the displacement. So at the final stage, okay, in any structure, although we sometimes you will see many problems that say you can say this simply supported beam is subjected to 100 kilonewton concentrated force at the midpoint. You can see a problem that simply supported beam is subjected to a 100 kilonewton force at the midpoint. Okay, so it does not mean in your problem you can see that the 100 kilonewton force is applied instantly to the beam. That is within few seconds. Within 1 second, the 100 kilonewton load is applied to the structure. But practically, it is not. Practically, the load will be applied gradually. That means at the initial case, force will be 0. Then force will be applied. Force will be applied at point, and it will be increased gradually. Gradually. Okay, so 100 kilonewton force will not be applied instantly. It will be applied. It will be applied from 0 to 100. That means at the very beginning, the applied force was 0. Then it will be 5 kilonewton, 10 kilonewton, 20 kilonewton, 25 kilonewtons, something like this, and ultimately the applied force will be 100 kilonewton. Okay, so to calculate the total force, you cannot say the applied force is 100. At the final stage, the applied force is 100, but to calculate the work, you have to calculate the average force. Average force is what? Initial force plus final force divided by 2. That is average force. If we consider the force is increased uniformly, okay, if we consider that the force is applied uniformly, that means in 1 second, at 0 second it is 0, at 2 second it is, so at 1 second it is 10, in 2 seconds it is 20, in 3 seconds it is 30, in 4 seconds it is 40. So it is increased uniform. In that case, to calculate the average shear stress, it will be average force. It will be the initial force plus final force divided by 2. So initial force is 0 and final force is for this element. Final force is delta F. So the average force will be delta F divided by 2. Okay, as initial force is 0. So this is the average applied force. And due to that force, the deformation in the body is epsilon delta Z. Epsilon is what? Epsilon is the strain along Z direction. Okay, strain along this direction. It is the strain. So strain is what? Strain is the deformation per unit length. Deformation per unit length. So what will be the deformation, total deformation along this length? As the total length is delta Z, so total deformation will be epsilon times delta Z, because this one is the deformation for one length and the total length is delta Z, so the total deformation will be this one. Okay, total deformation will be this one. So it means that this amount of force will be displaced by this amount of displacement. Okay, this amount of average shear force will be displaced by this amount of distance. So the work will be this force multiplied by this distance. That is the work. So it is what? It is the strain energy. Okay, it is the strain energy. So again, look at this figure. So it is sigma delta F. That means the applied force, which is applied force at the final stage. It will be sigma, that means the stress times area. Area is delta X times delta Y. This one is delta X. This one is delta X. This one is delta Y. So total force is sigma delta X into delta Y. Okay. And again, in previous classes, I told you that to develop any mathematical equation, we always consider some assumption. Okay, we always consider some assumptions. And similarly, to develop the strain energy equation, we have to consider assumption. So what is the assumption? Assumption means, say, if we apply any kind of force to any kind of structure, if we apply any kind of force to any kind of structure, then there must be heat generated. Okay, there must be heat generated. Okay, if we apply any kind of force to any structure, then heat must be generated. Okay, and heat is also energy. It is also energy. So basically, the applied energy or applied external work will be internal work plus heat energy. Internal work plus heat energy. That means external work equals to work stored in the body plus energy lost by heat generation. Energy lost by heat generation. But for this type of problem, the heat generation is very, very small. That means the energy due to heat generation is very, very small compared to strain energy. So we can assume that there is no energy loss due to the heat generation. Okay, there is no energy loss due to the heat generation. Therefore, the applied energy will be stored energy. Okay, applied energy will be stored energy, or we can say external work equals to internal work. External work equals to internal work, and that is strain energy. And as the element is very small, so what will be the energy stored in this element? We can designate it as delta U. Delta U is the energy stored in this small element. Okay, so that will be the force time displacement, and force is what? Force is delta into sigma into delta x delta y, and to determine the average force, it will be divided by 2. That's why it is half into force into displacement. That is the energy, strain energy. So you will see there are 3 terms: delta x, delta y, delta z. So if we multiply delta x, delta y, delta z, what does it mean? It is the, as it is a cubical element, it is a cubical element. So for this element, it indicates the, or it will give you, it will give you the volume of the element. Okay, volume of the delta x times delta y times delta z, it will give you the volume of the element. So we can represent it by delta v. Okay, delta v. Therefore, the delta u will be half sigma epsilon delta v. And if we divide both of this equation by delta v, then it will be delta v by delta u, and ultimately it will be epsilon half sigma epsilon. And this term is known as strain energy density. Why? Because it indicates that this is the energy stored in this amount of volume. Okay, it is the energy stored in this type of volume. So this, if we divide this total stored energy by the total volume, then we will get the energy stored per unit volume. Energy stored per unit volume. That's why it is known as strain energy density. Strain energy density. Then external work done due to different types of forces. Different types of forces, and sometimes the structure may be subjected to axial forces. Axial forces may be tension or compression. Okay, axial forces may be tension or compression. So if the structure is subjected to axial forces, then the external work UE, that is the external work, will be F into delta x. F is the force and delta x is the displacement. And if we integrate over 0 to L, that means over the whole length, then we will get the total external work, and that is according to the assumption that will be equals to the total internal work, and which is nothing but the strain energy. Okay, and if the material is linear elastic, that means stress and strains are proportional to each other for any kind of amount of applied force. Stress and strains are proportional. In that case, the equation of strain energy, total strain energy, will be half P delta. P is the applied force, delta is the total deformation. Okay, total deformation due to this applied force. And the external work due to a couple moment. That means the structure may be subjected to couple moment, that is torsion. Okay, torsion, and we know due to couple forces, the displacement will be rotation. Displacement will be rotation, and we know the work equals to force time displacement. Okay, force time displacement, and if the structure is subjected to, if the element is subjected to moment, couple moment M or torsion M, and due to that moment, due to that torsion, the displacement is delta theta. So the work will be force time displacement, that is M delta theta, and to determine the total external work, we have to integrate over the whole rotation, or entire rotation 0 to theta. So that is the total external work, and according to assumption, that is equals to internal work. This is strain energy, and similar to this one, for elastic material, the total strain energy will be half m theta. Half m theta. M is the couple. Okay, couple moment. It is not the bending moment. Okay, it is not the bending moment. Okay, then strain energy for normal stress. Okay, if the structure is subjected to normal stress, then what is the strain energy? Look at this figure. This figure, in this element, this element is subjected to a stress along z direction, sigma z, and the dimensions are given. So as the element is small, so the strain energy will be ui. Okay, dui, strain energy delta amount, that is small, very small amount, which will be half sigma x according to the previous equation, epsilon z dv. Okay, so yeah, so this equation indicates that the total strain energy or the strain energy depends on the volume. So to get the, or to determine the total strain energy, we have to integrate this equation. Okay, and integration will be integration will be done over the entire volume. That's why it is here. So this is the this equation will give you the total strain energy. Okay, total strain energy, and if the material is linear elastic, if the material is linear elastic, that means stress and strains are proportional to each other, then the equation of strain energy will be sigma square divided by 2e dv. E is the modulus of elasticity, and sigma is the applied force. And in this case, the element is subjected to uniaxial normal stress. Uniaxial normal stress, that means this element is sure. Any question? Okay. This stress is normal stress, and the element is subjected to the stress along one direction only. One direction. That's why it is known as uniaxial normal stress. That means one stress is acting along only one direction. Okay, and sometimes the structure may be subjected to shear stress. Okay, and this element is subjected to shear stress, and the value of shear stress is tau. And due to that shear stress, the shear deformation is shearing strain is gamma. Okay, shearing strain is gamma, and gamma is nothing but the tan theta, right? Tan theta. So if it is gamma, so it means that this length divided by that length. Okay, this length divided by that length, that is perpendicular by base. So this length will be gamma delta z, because this length is delta z, dz. Sorry, delta dz. So this length will be gamma dz. Actually, this point was here. Now it is here. That means this point has been displaced from this point to that point. So this is the total displacement. Okay, so the work will be what? Strain energy. Strain energy equals to what? Work done. So the total force times total deformation. The total force will be stress time area. Stress is tau, area is dy times dx. So tau dx by dy, and to determine the average force, divide by 2. and this is the total displacement, because this is force. Any question? Are you, anyone is talking or? Okay. This force has been displaced from here to here, so the total displacement is gamma dz, and after simplification, dy will be half tau gamma dv. Again, so this equation indicates that the strain energy depends on volume. So to determine the total strain energy, we have to integrate this equation over the whole area. So it will be this one, and for linear elastic material, the equation will be this one: tau square 2g dv. Tau square, that means shear stress square divided by 2g. So it is similar to previous one. There is a similarity. For normal stress, the parameter is modulus of elasticity, and for shear stress, parameter is modulus of rigidity. So the equations are similar. Only the terms will be different. For normal stress, it will be normal stress and modulus of elasticity. For shear stress, it will be shear stress and modulus of rigidity. But the patterns are same. Shear force square divided by 2e and force stress square divided by 2g. Okay, and sometimes if the structure may be subjected to multi-axial stresses, that means the structure may be subjected to stresses along x direction, along y direction, z direction, and all faces may be subjected to different shear forces. So for this type of problem, the total strain energy will be this one. This is the strain energy for the multi-axial stresses. So this equation is applicable for any kind of forces. So you can apply this equation for this case or for this case. Okay, you can apply the general equation for this case and this case also. So this is the general equation because this equation is applicable for any kind of stresses. And then elastic strain energy. Elastic strain energy, that means if the material is elastic, linear elastic. Again, I told you many times that the material is linear elastic. That means stress and strains are proportional. In that case, strain energy is known as elastic strain energy. Elastic strain energy. And if the structure is subjected to axial load, then the equation of strain energy will be n is 0 to L. That means integration over 0 to L. L means the length. N is the applied force. To AE. A is the cross-sectional. And dx is the length of the small segment. Okay, so this is the this equation give you the will give you the strain energy if the structure is subjected to normal stress. And if the structure is subjected to bending moment, then the elastic strain energy will be given by this one. It is integration over 0 to L m square 2ei by x. So it is similar to previous one. In previous one, it was applied force square divided by 2AE. Okay, a normal force. So and the parameters corresponding to normal force are this one, and this one is force is bending moment. Moment square, that means force square divided by T 2EI. I is the moment of inertia, and you will see that the moment of inertia is related to bending moment. Moment of inertia is related to bending moment. You will learn it by from your Nusrat Madam's lecture later. Okay, and if the structure is subjected to transverse shear, this one is the transverse shear, then the equation of strain energy is this one. Integration over 0 to L, F is B square, B is the applied shear force, 2Z is A, Z is the polar moment of inertia, shear rigidity, and there is a new term, Fs, and Fs is known as form factor, and Fs will be given by this equation. Okay, Fs is given by this equation. So in this equation, A is the cross-sectional area, I is the moment of inertia, and there are two terms, Q over T square. So T means the thickness. Okay, T means the thickness. And Q, what do you mean by Q? So again, you will learn it in details in your madam's class. So I will not explain in details here, but I will briefly show you what do you mean by Q. So if we consider, it is another geometrical properties. It is another geometrical properties. So if we consider this section, it is a cross section. The cross section is rectangular. The width is B, and this width is nothing but T here. This one is T. Okay, this T is nothing but this one B. So for this section, the width is B and the depth is H. Total depth is H, small h. And this one is neutral axis. Neutral axis means, again you will learn what do you mean by neutral axis. Neutral axis, that means at this location, there will be no flexural stress. There will be no flexural stress. That means there will be no stress developed due to bending moment. That is known as neutral axis. Neutral means no stress. No stress is here. That is neutral axis. And for rectangular section, neutral axis is located at the midpoint. Neutral axis is located at the midpoint. So as the total depth is small h, so the depth of this this depth will be h by 2, and this depth will be h by 2. Okay. Now, what do you mean by Q? Q means, if we consider any segment, this one is a segment, and Q means the moment of area of this area with respect to this neutral axis. That is Q. Okay, moment of this area with respect to this neutral axis. So if we consider this area, and area is A prime. Okay, area is A prime, and the distance from this point to that point is y. Actually, this the distance from this point to that point is y, and this one is dy. It is very small. Okay, dy is very small. So we can say from this point to that point, the distance is y. Okay, so what will be this point? This length. This length will be total. This length minus this one. The total length is h by 2 minus y. So this length is h by 2 minus y. Okay. So if we take the moment of this area about this neutral axis, the moment is what? Moment of area means area times the distance of the centroid of the area. Okay. So the area moment will be area times this distance. The distance of the centroid of the area. So centroid will be here. Okay, as it is a rectangular section, so centroid will be half of this length. Okay, so the distance will be this length plus this length. This length plus this length. So this length is y, and that length is half of this one. So y plus half of this one. And A is the area. So area is this one times this one. This length is B, and that length is h by 2 minus y. Okay. So after simplification, the value of Q is this one. So this is the this is Q. So what is Q? Q is nothing but the area of a moment of a area about the neutral axis. So important for final exam. Okay, because within this time you will learn what do you mean by Q very clearly. And the elastic strain energy for torsional moment. That means if the structure is subjected to torsional force, then the equation of strain energy is this one. Okay, equation of strain energy tau square T square. T means that torque divided by 2 jg dx. So look at the equations. There is a similarity. There is a similarity here. Applied force square to EI. So first of all, you have to understand what geometrical properties and material properties are related to what type of forces. So we know this one is the modulus of elasticity. Modulus of elasticity, and modulus of elasticity is related to axial stress. Okay, related to axial stress. So this one is normal force. So normal force is related to geometrical properties, cross-sectional area, and material properties, modulus of elasticity. Okay, and come to here. So here the bending moment, and the bending moment creates again normal stress. Okay, bending moment again creates normal stress. So the material properties will be G. Yeah, sorry, material properties will be G, and there is another term. The geometrical properties for bending moment is I. And for torsional force, the torsion of force square here, force square divided by G. We know the stress developed by the torsional force is shear force. Okay, shear force. Therefore, the material properties will be shear rigidity. Shear rigidity, and geometrical properties is J. J is the polar moment of inertia. Okay, polar moment of inertia. Okay, so to apply all of this equation, to calculate the total strain energy, we have to express all of this applied force in terms of variable length. X is the length, variable length. So we have to express all of this applied force, torsion, or bending moment in this equation, bending moment or axial force in terms of X, because all of these equations we have to integrate from 0 to L, that means over the length. So for this, we have to develop the equation of force. This one is nothing but it is nothing but the developed force. Okay, it is nothing but the developed force or internal force. So we have to express the internal force in terms of variable length. And how can we apply it? We'll learn by this problem. It is an example. Okay, it is a beam. And this beam has two reactions. One is at A, another one is at B. Two supports at A and B. And at A, the support condition is hinge, and at B it is roller. Okay, that means at this point, this support can resist the normal force and the shear force, and this support can resist only the normal force. And this beam is subjected to applied force, to an applied force P at point C. And the length of the beam is from A to B is L, and from B to C is L. And now we have to calculate the strain energy due to bending within this region. Okay, we have to calculate the strain energy. We have to calculate the strain energy due to bending within region A to B. Okay, that means how much energy will be stored. How much energy will be stored within A to B? How much energy will be stored within within the region A to B due to the bending moment developed by this applied force? Okay, developed by this applied force. So, which equation we have to consider? We have to consider this equation. Okay, it is bending moment, because we have to calculate the strain energy due to bending moment. So we have to apply this equation. To apply this equation, M is the internal moment. M is the internal moment. So we have to first of all we have to express the internal moment in terms of variable length. So to develop the expression of internal moment in terms of variable length, what will be the origin? Somebody can say, oh, okay, another assumption is EI is constant. E, that means modulus of elasticity. I is the polar moment of moment of inertia. So this term is constant over the full length of the section beam. Full length of the beam. Okay, so to develop the expression of bending moment, internal bending moment in terms of variable length, what will be the origin, or what will be the origin? That means from where the length will be measured. From where? Somebody can say we will measure the length from here. That means we will measure the length from here up to this point. And another student or another guy can say, no, I will not measure from here. I will measure from here at point B. And I will measure the distance from here and I will go to A. Because we have to measure, we have to integrate from A to B over this length. So you can, somebody can start from here to here, or somebody can come from here to here. So if one student goes from A to B, then origin will be A and upper limit will be B. And if another student starts from B and goes to A, then origin will be B and upper limit will be A. And another student can say, no, I will start from C. Okay, I will start from C. So if she starts, or if he or she starts from C, then he will, that means he will measure the distance from here, but he will go from B to C, B to A to calculate the strain energy. Okay, so what will be the result? What will be the result? Which one will be the correct one? Basically, actually, all will be correct. If one student can start from here to here, it will be give you one result. And if another guy starts from B to B and goes to A, it will give you another result. And if another guy starts from C, it will give another result. But ultimately, you will see that all three results are same. All three results are same. That means you can apply, you can consider any point as origin to measure the distance. Okay, you can. Equations, and we have three equations of equilibrium: summation of Fx, summation of Fy, summation of bending moment. As we have three equations, three unknowns, so structure is determinate structure. Okay, determinate and stable structure. So after solving, the reaction at A will be downward P, and reaction at B will be upward 2P. Okay, and this one is the applied force. Okay, and one guy can start from A. That means one guy can consider A as origin. In that case, the variable length is x1, and another guy can consider B point as origin. In that case, the variable length will be x2. But look at here. If one guy consider this point as origin, he will not go this way. He will not go this way. He have to go this way. He has to come this way, because we have to calculate the strain energy within this region. So variable length will be within this region. It will not be here. Okay. So if one guy consider B point as origin, then the variable length is this one, x2. Okay. And if another guy consider this point as origin, then the variable length will be x3. Okay, variable length will be x3, because x3 this x3 will not terminate here. Any question?
স্যার মাউসের কার্সার দিয়ে দেখালে ভালো হয় স্যার, তো স্যার তো বোঝা যায় না।
Okay, that means I am saying that if one guy consider C point as origin, then the variable length will be from here to here. You cannot terminate in this zone. To define x3, to define this variable length, you cannot terminate in this zone, because you have to calculate the moment in this zone, or you have to express the moment in this zone. So the this variable length must be in this zone. It will not be here. Okay, so we can go for one by one. So for first one, that means if one consider a point as origin, then what will be the strain energy? For this case, the range of the variable length is 0 to L. Okay, here from A to B. From A to B, that means the variable range of the variable length will be 0 to L. Okay, and to express the bending moment in terms of this variable length, we have to take a section in this zone. Okay, we have to take a section. So if we take a section here, you can consider left part or right part. Okay, but for this case, we can consider left part, because left part is little bit simplified. Right part is little bit complicated. So if we consider left part, so this one is the internal bending moment. Okay, this one is the internal bending moment. That means this amount of bending moment will be developed at this section due to the applied force. Okay, so what does it mean? This amount of bending moment will be developed at this section due to the applied force. Okay, so this is the free body diagram. This one is the reaction. There will be a shear force, and this is the bending moment. So to express the bending moment M1 in terms of x1, we have to take the bending summation of moment about this point or about this point. So if we take moment about this point equals to 0, okay, summation of moment about this point equals to 0, then clockwise, anti-clockwise positive according to sign convention. Anti-clockwise positive. So this one is anti-clockwise. This one is positive M1, and this reaction will develop anti-clockwise moment. Okay, develop anti-clockwise moment. So it will be also positive. So and its value will be P times x1. Okay, P times x1. So M1 equals to minus P times x1. So this is the expression of bending moment. This is the expression of internal bending moment in terms of variable length. Okay, this one is the variable length. Okay, so we have the equation. The general equation of strain energy due to bending is mo square dx over EI. So m square is m. So substitute this expression here. EI is constant. Okay, according to the given condition of the problem. So EI is constant. We can take this out, terms outside the integration sign. And what will be the limit of the x? Limit of the x will be 0 to L. 0 to L, because we have to start from A and we have to reach to B. So x is measured from here. So length will be range will be 0 to L. So here the range is 0 to L, and after calculation, the equation of strain energy is P square LQ over 6EI. Okay, and go to the next origin. If another guy consider B point as origin, okay, B point as origin, that means x. In that case, the variable length is designated as x3. You can say it is x, no problem. It does not mean necessary that you have to again choose x1, x3, x4, etc. You can say it is x. So here the value of x is 0, and you have to reach to A. You have to reach to A. So at A, the value of x2 will be L. So the range of the variable length will be 0 to L again. And to calculate, to express the internal moment in terms of variable length, you have to again take the section, and you have to consider any part, left or right part. So we can consider right part for this case. So this is the internal moment, clockwise moment. This is the shear force for free body diagram. And this one is the reaction at point B, and it is the applied force. So again, to express the moment, you have to apply summation of moment. So we can consider the summation of moment about this point is 0. Okay, so this one is clockwise moment, so it will be negative. This one is clockwise moment, negative, and this one will create anti-clockwise moment, so it will be positive. So its value will be 2p times x2. So 2p times x2. And this force will create clockwise moment, so it will be negative, and its value will be p times this distance. Okay, p times this distance. So this distance, this one is L, and that one is x2. So the moment will be p times L plus x2. P times L plus x2, and it is negative because it is clockwise direction. So the expression of internal moment in terms of variable length is this one. Again, substitute this expression in the original equation, and after simplification, take this time outside the integration side, and the limit of integration will be 0 to L. Okay, 0 to L. And after simplification, the equation is equation of strain energy is P square L over 6 EI. And for the third case, if another guy considers C point as origin, then we have to express the internal moment in terms of variable length. Here, variable length is mx3. So this one is clockwise moment. So if we apply the summation of moment about this point equals to 0, so this one is clockwise negative moment, and this one is produced anti-clockwise. It will be positive. So it will be 2p times this distance. Okay, 2p times this distance, and that distance is from here to here it is x3, and here to here it is L. So from here to here it will be x3 minus L. Okay, so that's why it is x3 minus L, and this one will create or develop a clockwise moment. It will be negative. So minus p into x3. Okay, so this is the expression of internal moment in terms of variable length. Again, substitute this expression in the final equation, and after and now what will be the range of this variable length? Okay, what will be the length of this variable length? Go to the previous, initial problem figure. So although the x3 starts from here, but you have to calculate the strain energy within this range. So if you start from here, actually to calculate the you have to calculate the strain energy within zone B to A. You have to integrate from here to here. You have to integrate from B to A. So at B, value of x3 is L. Okay, value of x3 is L. That means the variable length will start from L, and at point A it will be L plus L, 2L, because it is another L plus L, 2L. If you start from here, the variable length will be from B to A. So at B, variable length is this one, and at A, variable length is this one. So it will be L to 2L. Okay, so that's why it is integrated over L to 2L. And after calculation, the equation is P square L cube over 6A. So look at all of these three equations. So it is PL over TI, P square L cube 6EI. This one is P square L cube 6EI. This one is P square L cube 6EI. Okay. So for all cases, the equation of strain energy is same. Okay. So actually, the purpose of showing three cases to make you understand that you can choose any point as origin to measure the variable length. It will not affect the final result. Okay, so do not worry about that. If one student can choose this one and another student can choose at this point as origin, it will not affect the final result. You can consider any point as the origin to measure the variable length. Okay, so that is the end of this topics. So there are other problems. I have explained one example or one problem, but you will in a class state and in final exam you will see other types of problem, but all are same. All problems are same. In case of axial force, you have to express axial force in terms of variable length. In case of bending moment, you have to express bending moment in terms of variable length. In case of shear force, you have to express shear force in bending moment, variable length. In case of torsion, you have to express internal torsion in terms of variable length. Okay, our procedures are same for all cases. Only the applied force will be different. For this case, The applied force is bending moment. For other types, it may be axial force, and for other types, it may be torsional force. But the procedures are same for all cases. Okay, so you have to practice for other types of forces, and I am following the Hibbeler book. Okay, Hibbeler, you can also follow that book if you want, or if you can also choose other books also. And any question? I think you have no question.
স্যার আসসালামু আলাইকুম স্যার।
হ্যাঁ বলো।
স্যার স্যার আমার রোল 120 স্যার।
হ্যাঁ 120।
স্যার আমার এখানে স্যার সকাল থেকে কারেন্ট ছিল না তো স্যার, তো আজকে ক্লাসটা যদি স্যার একটু রেকর্ডটা যদি আপলোড করে দিতেন স্যার দয়া করে।
আমি এই এখনই আপলোড করব, এখনই আপলোড করে দেব, তোমরা সবাই পেয়ে যাবে।
স্যার ওই আপনার স্যার রেকর্ডে স্যার ওই আপলোড যে করেন স্যার মাঝে মধ্যে স্যার ওই আমাদের অ্যাক্সেস চাই স্যার, এটা প্রবলেম করে স্যার, একটু দেখে আপলোড করে দিন স্যার যেন কাউকে অ্যাক্সেস
আমি ওই যে লেকচার নোটটা আপলোড করে দেব, ওই লেকচার নোটটা দেখলেই বুঝতে পারবে।
আচ্ছা স্যার আচ্ছা স্যার, রেকর্ডটা দিলে একটু ভালো হয় স্যার, বুঝতে
হ্যাঁ ঠিক আছে
স্যার।
স্যার লেকচার নোটটা আপলোড করলো।
তাহলে 9টা 20 ক্লাস টেস্ট, সবাই কিন্তু জুমে এসে ভিডিও অডিও অন করে রাখবা, আর কিন্তু পরীক্ষাটা দেবা জুম ক্লাস গুগল মিটে, গুগল ক্লাসরুমে।
স্যার কয় তারিখ স্লাইডটা একটু আপলোড করে দিলে ভালো হবে স্যার।
হ্যাঁ ফাইলটা এখনই আপলোড করে দিচ্ছি।
স্যার ক্লাস টেস্টটা কয় তারিখ?
ক্লাস টেস্টটা হচ্ছে 30 তারিখ বুধবার 9টা 20। ঠিক আছে, তাহলে ভালো থাকুন। আর এটাই আমার লাস্ট ক্লাস, এরপরে আর কোন ক্লাস হবে না যদি আমি না বলি। ঠিক আছে, ওকে, সবাই ভালো থাকো।